Welcome back, everyone. We're continuing with Chapter 9, notes on atmosphere and atmospheric processes, and this is going to be Section 2 we're going to be continuing with. So if you recall from Section 1, we talked about the various different ways that heat and energy are transferred around the atmosphere, and one of those ways was radiation. And we're going to be focusing a little bit more on radiation right now in this chapter. And when we say radiation, we actually should be more specific. We mean electromagnetic radiation. Electromagnetic, all one word. All right, that is, you might say that the light, the visible light that you can see, is electromagnetic radiation. There's going to be varieties like infrared and ultraviolet. All these are types of electromagnetic radiation. And the way that is transferred around the atmosphere helps drive a lot of these atmospheric processes. The sun gives out all kinds of electromagnetic radiation. So the sun is over here, okay, shining nice and bright. Right here, the Earth is, let me change the blue here, make a little blue marble right here, okay, millions and millions of miles away, and the sun gives out all kinds of radiation in all directions, all right? Only a teeny tiny bit of it actually gets to us. A lot of it is lost into space and contributes to lighting up and heating the other planets and all kinds of other things. We only get a little bit of the sun's radiation, and even the radiation that hits us, that hits our Earth, doesn't always make it down to the Earth. But that radiation that, and we'll talk about that in just a second, but that radiation that does drives virtually everything that we can see and observe in our atmosphere. We have the hydrologic cycle, the fact that water evaporates and then condenses and runs downhill, and the whole water cycle. That's driven by the sun. Waves and currents, driven by the sun. Even atmospheric circulation, which we'll look at later on in this chapter, how air rises at the equator and sinks at the poles, is all driven by the sun. So, what are some varieties of this? Right there yet? Well, I guess we are right there. What are some varieties of this electromagnetic radiation? Well, they vary by their wavelength. All right. Now we can think of electromagnetic radiation as being waves. Right? That's not a very good wave right there. Don't think of waves as an ocean, but think of like waves, like I guess like energy waves, maybe. All right. How is that wave different from this wave or this wave right here? Well, you can see that their wavelength is different. They're all the same type thing, but they have different wavelengths. You have a lot of little wavelengths right here. This is a medium wavelength, and here's a really long wavelength. They all travel at the same rate, all right? But for a certain amount of time, let's see, let me change colors right here. Let's say from here to here, they may go from here to here at the same rate, but you get a lot more waves with this one than you do with this one right here in a certain amount of time. So all the different varieties of electromagnetic waves are determined by what we call their wavelength. All right, and then the next slide will kind of show that. So this sort of shows all the different varieties of electromagnetic waves that are emitted by the sun. Like I was doing before. Let's see here. I'm going to make these red. I was drawing different waves, and so we had this whole spectrum right here of different kinds of waves. The longest ones are radio waves. All right, very, very long waves that are they're low energy. They pass through you. They're passing through you right now. In fact, they're what makes your cell phone work. And they don't hurt you because they are low energy. They travel at the same speed as the rest of them, but they have less waves for a certain amount of time, so they're lower energy. As we move up this direction, up the electromagnetic spectrum, the waves get a little bit shorter. Okay, it's supposed to be shorter right there. Okay, TV, FM, and radio, shorter still. That's supposed to be shorter too. All right, microwaves, shorter. Infrared, okay. Infrared waves are what you feel as heat. as heat. And we've got a heat lamp in class that even if you have your eyes closed, you can feel that radiation because you feel it as heat. So it's giving off light, visible light, which is the next one we'll talk about, but it's also giving off infrared, which you can feel even if you had your eyes closed. Now, visible light. In class, what we did was we took various different colored pencils, and we broke this visible light into a variety of different wavelengths and colors. It starts with red, all right, and red is very close to infrared right there. But as we move up, now I'm not going to do red, orange, yellow, green, but I'll do red, green, and blue. As we move up, the wavelengths get shorter and shorter and shorter. And the colors get more and more blue, or move more and more towards the violet end of the spectrum right there. So those three waves are supposed to be getting shorter and shorter and shorter wavelengths. But this spectrum, this visible light, is what we can actually see. The reason you see a rainbow when you look through a prism is because a prism, oops, I shouldn't do that, because a prism breaks apart the colors of visible light into their components, so you see what looks like a rainbow. Well, if we go too far off the end of that spectrum, I'll change to purple right here, we have what's called ultraviolet. Now you can see purple, but you cannot see ultraviolet. Ultra means above. So it's like violet, but it's above violet, so you can't actually see it. All right, so that is invisible to us, but our bodies can detect that because that's what gives you, well, it gives you a tan, but it also gives you skin cancer as well. So we need to be protected from ultraviolet like the atmosphere does for us. X-rays. You definitely want to limit your exposure to X-rays. All right, because there's a lot of wavelengths, all right, and so that means you've got more energy coming in, so they can actually cause cancerous damage to your body. Gamma rays. I'll make these even shorter, and as you see, these wavelengths are getting shorter and shorter and shorter. Very close together waves. Gamma rays are very, very harmful to you because you've got a lot of waves coming through in a certain amount of time. And finally, cosmic rays. At some point you can't even draw these waves right here, but they're so close together, all these wavelengths, that they're so teeny tiny. Look at these sizes right here, all right? Millionths of a millimeter. Up here, radio waves, we've got kilometers long. So all these waves vary by their wavelength, but the variety that we can see is visible light, and that's what gives us the colors that we can actually see. So all these different waves interact with the atmosphere in different ways. First of all, what's one way it can interact with the atmosphere? Well, it can be redirected back out to space. I'll change to red right here. All right. So you have the atmosphere. We'll say we have the Earth. Okay, right here. We have the atmosphere kind of above it right here, and we've got not a very good atmosphere. Let's do that again. A little bit better, okay? And we have radiation coming in from the sun. Well, one thing that can happen is it can be, first of all, reflected back out to space. The atmosphere is somewhat reflective to a degree. So that's why we say that can happen. It can also be scattered as well, which means the atmosphere, sometimes you'll see it looks kind of hazy, right? If it's hazy, what that means, what's happening is that the light coming in from the sun, the light that you can see and other varieties of light that you can't see, are being scattered through the atmosphere. So this original ray of radiation doesn't come straight through, but kind of spreads out through the atmosphere. The other thing that can happen is that it can be transmitted through the atmosphere. That means like the atmosphere behaves like glass, and that's a good thing. Let's say we have a different kind of radiation coming in. The atmosphere might be perfectly transparent to that, and it will come right down to the surface. Great. So that means that energy can be used to do some sort of work on Earth's surface. The third thing that can happen is that it can be absorbed. And our atmosphere is very good at absorbing certain kinds of radiation as well. One kind that it absorbs pretty well is infrared. And looks like I already used red, but I'll change to, heck with it. You know what? It also absorbs ultraviolet. So yeah, we'll do that. Let's say ultraviolet comes in. It might just be absorbed by the atmosphere right there and not even make it to the ground. That's actually good. Our atmosphere does that because ultraviolet can give you cancer. So 3 different things can happen to the radiation that comes from the sun once it strikes our atmosphere. All right. Depending on how much energy gets to the ground, whether it's absorbed by the atmosphere or reflected back out, that'll determine how much temperature you feel. One thing that's interesting is that let's say we have the Earth right here, and you've got some clouds. Okay, you've got some clouds here. So here's your house, and maybe your friend lives over here in Europe or something like that, and they don't have clouds. All right, so 2 different places on the Earth, one with clouds, one without. You probably may have noticed, especially on winter nights, that if it's a cloudy, overcast night, it's going to be maybe a little bit warmer. All right, because as the Earth receives radiation and kind of reflects it back out, a lot of times clouds will trap that. And so if it's overcast, it'll feel warmer. If it's a completely, if it's a completely starlit night, okay? I know stars aren't black, but all right, a completely clear night. Don't you notice that it tends to be a lot colder, right? Why is that? Well, because energy can get right back out. If it's a really clear night, energy can get back out. You don't have these clouds that act like a blanket. Energy just escapes back out to space, so it feels a lot colder. So depending on how energy is either absorbed or reflected, that'll determine what you experience on Earth's surface in terms of temperature. So reflection depends on a property that we call albedo. All right, and albedo, I know that sounds like the name of like a mobster or something, but yeah, albedo is you might say the reflectivity of a surface. All right, white, something that's white has a high. Oops, that's not white. That's red. Well, I can't really draw white on white, but high albedo, right? Because it's reflective. This right here has a low albedo. Something that's black or something that is dark has a low albedo. It does not reflect light as well, or at least not visible light. So depending on how it reflects radiation back, that determines the albedo. When we talk about absorption, of course, that is the surface actually takes it in and doesn't reflect it at all. But usually what happens is that if a surface, let's say a dark surface, all right, like say a black piece of paper, and let's say we shine some white light on it. Now I can't really, like I said, I really can't draw white light, but I'll just draw it like it's green, okay? So this is visible light right here, shining on it from the sun. That surface may absorb that white light, or I drew it as green, but that greenish white light, okay? But that's not the end of it. If a surface absorbs one kind of wavelength, one kind of radiation, what it also means is that it re-radiates or it reflects a different variety. So it can't just keep taking in energy. It takes in one type, but it gives out a different type. So it might absorb visible light, which, by the way, that's why things that are black look black, because they absorb white light and they don't re-reflect it. But it might re-radiate infrared. It might re-radiate infrared. Well, what do you experience as infrared radiation? Well, you feel heat, right? How many times have you been on a blacktop parking lot, which looks black because it's absorbing white light, but it's really darn hot because it's giving off this infrared radiation? That's what's happening right there. So if a surface, any surface, absorbs one kind of light, it's going to give off another kind of light or another kind of radiation, and that's what makes that work. Right here, this diagram is just sort of a summation of what I just kind of talked about, all the various different ways that energy can be transmitted around the Earth, around the atmosphere, coming in from the sun right here, being reflected back out to space, absorbed by the Earth, absorbed by the atmosphere, lost back to space, scattered, all kinds of things that the atmosphere does to radiation as it is struck by radiation from the sun. So these are things that we'll continue to talk about, but this section right here is focused mainly on how radiation moves around the atmosphere and how it contributes to those large-scale weather events that we're going to talk about. So I thank you for your attention. I will ask you if you have any questions to make sure you see me. And for the meantime, thank you for watching, and I'll see you on the next one.